In the last class, we were discussing cascading of amplifiers. Let us now take an example so as to illustrate the effect of cascading. An amplifier A with Ri, the input resistance, equal to 10 kilo ohm, and R naught equal to output resistance of the amplifier 5 kilo ohm, has an open loop gain, that is at the output, load is open, okay, open loop gain of 100. It is cascaded with another identical, that means the other amplifier has the same value of Ri, R naught and open loop gain. Identical means same value of Ri, R naught and open loop gain. Identical amplifier B, we will call it B, full stop. The source has a resistance of 4 kilo ohm. This is the source driving the first amplifier. The load resistance for the amplifier B is 5 kilo ohm. Determine the overall voltage gain, current gain and power gain. That is the problem. Let us see pictorially how this cascading looks like. We have the source with source resistance of 4K connected to amplifier A. At the input it has 10K input resistance. Now that amplifier has an open loop gain which is 100 times Vi1. Vi1 is the input to amplifier A. So 100 times Vi1 and a series resistance, output resistance of 5 kilo ohm. It is connected to another amplifier. The load for this amplifier is going to be the input resistance of the next amplifier. So that is 10K. And it has a gain 100 times Vi2 as the gain from here to here, open loop gain, and a series resistance of 5K and a load resistance of 5K. This is the pictorial depiction of the problem. So how do we now solve? What? For example, we would like to know V02, which is the final output voltage, divided by Vs. This is one voltage gain we would like to know. Another voltage gain is V02 divided by Vi1. This is the overall amplifier voltage gain. This we have defined. This is from the transducer, the voltage gain, right, including the source resistance. So then we would also like to evaluate I02 final output current here flowing through the load divided by I1, which is the current gain. I02 divided by I1, current gain. If I have represented this as a current source in shunt with an impedance, I would have had I02 divided by Is. Okay, that is another gain corresponding to this. You can leave it like that. Then we have the power gain P0 divided by P0 divided by Pi, which is P0 is this voltage at this point, V02 into I02. Okay, see, V02 into I02, and Pi is going to be Vi1, okay, into II1. So it is very clear that if we evaluate the current gain, this one, and the voltage gain, this one, we will get the power gain. So this is just multiplication of what we are given. So basically we have to evaluate this, this and this, right. This is self-explanatory. Now we will do it step by step. First let us go from here, Vi1 divided by Vs. What is it? Vi1 divided by Vs is 10 divided by 10 plus 4, that is already evaluated. Then let us evaluate V naught 1 by V I 1. Now, what is V naught 1? You have 100 times V I 1 coming here. So, 100 times V I 1 comes here straight away. That source is going to have the voltage divided between this 10 k and 5 k. So, we have 10 k divided by 10 k plus 5 k, 15 k. So, that is equal to what? V naught 1, which is the same as V I 2. V naught 1 is the same as input to output of this is same as input to the second amplifier. So, we have evaluated this. So, V naught 1 divided by V I 2, V I 1 or V I 1 is going to be equal to 100 into 10 by 50, which is also same as V naught 1 by V I 2. Okay. So, this is not yet over. We have only partially evaluated the gain from here to here. We have to come to this stage now. So, just a minute. V naught, this is not correct. V naught 1 by V I 1, and V naught 1 is same as V I 2 divided by V I 1. Okay. V naught 1 is same as V I 2. V naught V I 1 this. Okay. Now, coming to this stage, 100 times V I 2 comes here. Out of which only portion appears here, 5 k and 5 k. So, 5 divided by 5 plus 5, which is 10, is going to be equal to V naught 2. Once again, V naught 2 divided by V I 2 is equal to 100 into 5 by 10. So, now we are in business. We want V naught 2 divided by V I 1 as the gain, which can be written as V naught 2, that is the final thing, divided by V I 2, okay, into V I 2. So, V I 2 gets cancelled, okay, divided by V I 1. Is this clear? V naught 2 by V I 1 can be written as V naught 2 by V I 2 into V I 2 by V I 1 mathematically. So, this is simply multiplication of these two factors, which we have already evaluated. V naught 2 by V I 2 is given there as 100 into 5 by 10, yes, into the other portion V I 2 by V I 1 has already been evaluated as 100 into 10 by 15. Now, this is very easy to evaluate. 253, right. So, 200 into 50 200 into 50, so 10,000 by 3, right. So, this is that is the voltage gain. 3333.3 is the voltage gain, overall voltage gain. And if we want V naught 2 by Vs. We know that V naught 2 by Vs is nothing but V naught 2 by Vi1 into Vi1 by Vs. So, which we have already evaluated, Vi1 by Vs is 10 by 14, and therefore, this is 333.3 into 10 by 14. That is the voltage gain. So, the overall gain V naught 2 divided by Vs therefore equals 3333.3 into 10 by 14. How much is it? 2380.9. So, that is the overall voltage gain. Now, we would like to evaluate the current gain in a similar fashion. This we will try to evaluate using the information about voltage gain. Let us see. We know that Vi1 is equal to II1 into 10K. This is so basically we have II1 equal to Vi1 by 10K, and V naught 2 is going to be 10K, that is 5K, the load resistance, into I naught 2. Now, this is plus and minus, therefore, there is going to be a negative sign really speaking. So, I have assumed this as positive and this as negative. If I say I naught 2 is flowing like this, it will develop a drop here plus and minus. So, that is the meaning of the negative sign. V naught 2 is this. So, I naught 2 is equal to minus V naught 2 divided by 5K. So, what we want to now evaluate is I naught 2 divided by II1, I naught 2 divided by II1. So, that is going to be equal to minus V naught 2 by 5K, that is I naught 2, and II1 is Vi1 by 10K. That means it is minus 2 times the voltage gain V naught 2 by Vi1, which we have already evaluated as 3333.3, which is minus 6666.6 with a negative sign indicating, this negative sign is important, let us understand. II1 is going in and II2 has been assumed to be going in. So, actual current flow is opposite to that of what I have assumed. That is the meaning of negative sign. That means I naught 2, if it is this sign, the actual current is going to flow in the opposite direction. Therefore, I naught 2 and II1 are actually having a phase difference of 180 degrees or a negative sign. Okay. So, this is the current gain, and therefore, the power gain, which is P naught by Pi, therefore, is equal to the voltage gain V naught 2 over Vi1, which is 3333.3 into I naught 2 by II1, magnitude of this. So, this into 6666.6. Okay. This expressed in decibels, because this is a huge quantity, right. So, let us express this as 10 log to the base 10 of this factor, that is the power gain expressed in decibels. So, P naught over Pi in decibels, which is 10 log natural, that is not natural log, 10 log to the base 10 of this. So, how much is that? 73.46. So many decibels is the power gain, which is 10 log of log to the base 10 of this. Now, let us try to understand the concept of amplifier more thoroughly, more mathematically, more quantitatively than before. Okay. We will now go into linear two-port network theory a little bit, so as to understand how we can link what we have learnt in networks with what we are going to do with amplifiers. This we have already done. We have defined a two-port network in the following manner. It has input voltage, input current, output voltage, output current. A one-port network, linear, it has a voltage and a current. Now, some kind of mathematical concepts here. If V is independent variable in a one-port network, if V is independent variable, what does it mean practically? If I am going to fix V by means of a voltage source, a battery, right, I is going to be determined, or I is going to become dependent variable. That means, if I fix the voltage here, then I is dependent upon the property of the device here. Let us call this R, or let us call this G, conductance, right. So, G into V is going to be I. That means, if V takes on different values, I is automatically determined by the device that we are connecting. So, this is called independent variable. This is called dependent variable. That means, if I connect a voltage source, the current is always going to be dependent upon the G parameter. That is left to me actually. Why should I take V as independent variable? I can, on the other hand, say I is independent variable. That means, I can force certain current into the element here, one port, then V is going to be determined as I into R. Okay. So, R is going to be 1 over G here, the relationship. The resistance is 1 over the conductance. So, V is equal to I over I into R. So, I is independent variable, then V is dependent. So, this is what we have to understand. What is independent variable and what is dependent variable? This is for the one port. There are two parameters here, two variables, V and I. Okay. If one is independent, the other is dependent. Okay. Let us now consider the two-port parameters, actually, two-port variables. The variables are Vi, II, I0, V0. There are 4 variables, out of which any 2 can be independent variables. There are 4 variables which are Vi, II at the input port, V0, I0 at the output port, 4 variables, out of which any 2 if chosen as independent, the other 2 become dependent variables. Just as in the case of one port, if one is taken as independent, other becomes dependent. In two-port network, there are 4 variables. I can select any 2 of the 4 as independent variables. The other 2 become dependent variables, in which case there are basically 4 ways of defining the relationship between these different variables. There are 2 ways. Okay? For one port there are 2 ways. For 2 ports there are 4 ways. And all these 4 ways were exposed to you in networks. Let us see what these are. Let us consider the first way. I am considering that V0 and Vi are dependent variable. They are dependent upon I0 and II. That means they are functions of I0 and II. This is any function, right? But we are discussing about linear two-port network. That means they are linear functions. Okay? This relationship says it can be any function, functional dependence. So V0 is going to be linearly related to I0 and II. Vi is going to be linearly related to I0 and II. So in which case, what is it going to be? V0 is equal to I0, okay, I into something plus I0 into something, factor, linear dependence. What are these factors? This is a voltage and this is a current. Current into impedance. Current into impedance is voltage. So dimensionally this is impedance, though impedance is normally given as Z. So these parameters are called Z parameters. So this will be Z, this also is Z. Let us see what this is. This is relating output voltage with input current. Okay? This is relating output voltage with input current. This is relating output voltage with output current. So this is called Z0, which is really the open circuit output impedance. This is V0 and I0. Okay, we will see this. V0, okay, and I0 are related by this factor Z0. When will you get Z0? If II is 0. If II is 0, then we can get Z0 as V0 by I0. This is therefore called open circuit output impedance, right? So these are all called open circuit parameters. That means these parameters can be defined by respectively open circuiting input or output. Why? Because the dependent variables are V0 and Vi, independent variables are I0 and II. So those independent variables can be made respectively 0, and then for example this is an independent variable. If II is made 0, I can get Z0. If I0 is made 0, I can get this. What is this? This is giving you output voltage okay, when there is a certain input current. This is what is called, okay, the forward transfer parameter. Something happens at the output because something is happening at the input. Okay. So, this is called the forward transfer parameter. This is called, okay, the open circuit output impedance. This is called forward transfer impedance, right. So, this F indicates forward transfer from input to output, it is transferring transfer impedance. Remember this, we have already discussed this parameter, okay, earlier. We called it transfer impedance, forward transfer impedance, okay, or resistance. At that time we kept it restricted to resistance. Now it is more general, it is impedance. This is output impedance. Both these things are measured, okay, respectively with this. This is measured when output is open, okay, V0 is going to be open circuit voltage, and this is measured when II is 0, that means input is open. In order to measure this, we have to have I0 equal to 0, which means output is open. Okay. In order to measure this, output is open. In order to measure this, input is open. Okay. Now, it is very easy for you to compose the other linear equation. This is for V0. Vi equals, in a similar fashion, something connected with II plus I0 into the impedance. So, this is again Z parameter. Now, again let us see whether you people can themselves indicate what suffix we must give to this. Look at this. Vi is related to II. So, this is Zi, totally input port dependent. Vi is equal to Zi into II. So, this is nothing but input impedance. When do you measure it? When I0 is 0, which means output open. It is input impedance with output open. Now, finally, we have discussed this parameter also earlier. We have discussed this, we have discussed this, we have discussed it when we discussed the ideal amplifier. Let us see what this is. This is something we had not discussed, right? But we indicated here. This is what is developed at the input as voltage because of a current at output. That means this is the reverse transfer parameter. From output it comes to the input. So, this is the reverse, or just like the forward, this is the reverse, okay, transfer, or it is also called inverse transfer parameter, right. In this case, impedance. All the parameters in this case. How do you measure this? Again, II has to be 0, which means input open. Now, this is a complete definition of this block. Okay. in terms of what are called open circuit impedance matrix. Where is the matrix? So now this is a linear relationship. Therefore, if I represent this as dependent variable and independent variable, okay, then I can represent this in the matrix form in the following way. Let us see how this is going to be looking like. This is the port. I can put the matrix here, right? Zi, Zr, Zf. So we have to call this Zr, okay, because it is the reverse transfer impedance. And multiplied by I naught. This is equal to Vi V naught. Or this could be also written as V column matrix, okay, is nothing but Z. This is the impedance matrix into I, again a column matrix. So this is the matrix representation of the parameters, without really going into anything regarding amplifiers. This is valid for any linear two-port network. Now what I am saying is, let us understand this and now see what this can lead to in terms of amplifiers. This is the general representation of any two-port network which is linear. What is an amplifier? Let us understand. Ideal amplifier. Ideal amplifier is one which is unilateral first. Ideal amplifier, as defined by us earlier, we just said it is unilateral. What does it mean? There is transfer only in the forward direction. There cannot be transfer in the reverse direction. Then what does it mean? One of the parameters here is definitely 0. What is it? The reverse transfer parameter. That means in any ideal amplifier represented in any fashion, in any matrix, the reverse transfer parameter is 0. That means Zr is 0. So I am defining it and then making it 0 in order to illustrate what is really an amplifier represented in a two-port theory. So the reverse transmission should be going to 0. Now, if reverse transmission is 0, Zr is 0, and Zf alone exists, and what about Zi and Z naught? In an ideal amplifier, Zi has to be 0 and Z naught also has to be 0. So you will see that an ideal amplifier matrix representation is nothing but 0, 0, 0 and Zf. What is that amplifier? This is, look at it, what is Zf? Output voltage in terms of input current. So this is the trans impedance amplifier, which has been earlier called trans resistance amplifier, right? So a trans impedance amplifier is truly an ideal amplifier. Okay. So this particular amplifier that is defined by Z parameters is a trans impedance amplifier. Is it clear? Trans impedance amplifier. Now, you can easily come up with other equivalents for that. Dual of this, dual of impedance is admittance. Dual of impedance is admittance, which means when will I get that? When instead of Vi and V0 as dependent variables, I will take II and I0 as dependent variables, and instead of II and I0 as independent variables, I will take Vi and V0 as independent variables. So, we will now go towards the other type of amplifier. We were exposed to Z parameters. Now, let us see the dual of that, Y parameters or admittance parameters. These are called admittance parameters or Y parameters. Earlier, they were called impedance parameters or Z parameters. Let us see. Again, it is very simple to formulate now. The independent variables are Vi and V0 as against II and I0 earlier. So, Vi and V0 are independent variables and II and I0 are dependent variables. What it means is II and I0 are expressed in terms of Vi and V0. So, that means II is some Y into Vi, again Y some other to V0, Y into. These Y's have to be respectively defined now. All these are admittance parameters. Dimensionally they are admittances. So, II related to Vi, again it is input, okay, totally. That means Yi. And how does that get measured? When V0 is 0. So, either Vi should be 0 or V0 should be 0 in order to measure all these parameters. That means these are called short circuit parameters as against the earlier parameters which were called open circuit parameters. So, I make V0 0, then I can measure Yi as II by Vi. That is called short circuit admittance, input admittance. So, short circuit input admittance. This is Yi. Now, II is related to V0. That is, when there is something applied at output, that gets translated to input as II. When Vi is 0, that means input is shorted and the current flowing in the input because of the output voltage is called reverse transfer admittance. Okay, so this is YR it is called. Okay, this is the reverse transfer admittance. Coming to this, again you can see I0 output current is related to input voltage when V0 is 0, output is shorted. That is output current when output is shorted. Okay. So, relationship with input voltage, that means this is the forward transfer admittance. Therefore, YF it is called forward transfer admittance. It is the same as what we have discussed in the amplifier, okay, forward transfer conductance. We took it as conductance, here it is more general, admittance. So, finally, this is output current related to output voltage. So, totally output parameters, so Y0. when input is shorted. So, this is called short circuit output admittance. Short circuit output admittance. So, these are all short circuit parameters, and therefore, I matrix can be represented as Y matrix into V matrix. Okay. So, that means I naught is yi yr yf y naught vi. This is the matrix representation of y parameters. The same equations that we have written, the linear equations, can be represented by matrix this way. And what is this? This is a generalized way of representing any two-port network, which we have learnt in networks, but we would like to relate it to amplifiers. So, an ideal amplifier of this category is one where YR is necessarily 0, that means it is unilateral. And subsequently, we must have the other parameters yi and y naught also equal to 0. The only thing that can exist is yf is finite. And such an amplifier we have called as trans admittance amplifier, which we have earlier called as trans conductance amplifier, as against the Z parameter defined amplifier, which is trans resistance amplifier or trans impedance amplifier. This is called trans admittance amplifier. This is going to give you primarily a voltage controlled current source. This one will give you a current controlled voltage source, ideal. This is ideal. That is it. Now, one would say that these two amplifiers are more basic than the other two amplifiers. What are the other two amplifiers? Voltage controlled voltage source and current controlled current source. Why? You can see this is voltage controlled current source and that is current controlled voltage source. I can cascade these together. Voltage controlled current source is cascaded to current controlled voltage source. This is a current source feeding a current control block, very nicely matched. Current source feeding a current control block. What it means is current source, so source with infinite impedance, okay, feeding onto a short circuit. It is very good here, right? And therefore, this block now becomes what? A voltage controlled voltage source. So, I can get a voltage controlled voltage source by cascading ideal voltage controlled current source with current controlled voltage source. And what is the voltage gain? Because this should give a voltage gain. If this is voltage controlled current source, this is a trans conductance amplifier or trans admittance amplifier. So, this is defined by Y f, okay. This is defined by Z f prime, let us call it, because these are different parameters. Here it is to indicate that Z f is not 1 over Y f, it is different. So, this is YF, this is ZF prime. So, voltage control voltage source has a transfer parameter which is YF into ZF prime ratio. This is nothing but your so called K or whatever it is. Now, this is not all. You can get current control current source ideal by first putting current control voltage source, cascade it with voltage control current source. So, look at it. This is a voltage source, that means source resistance is 0 feeding on to a voltage controlled block which is infinite impedance, right. So, very nicely matched here, right, and therefore, this is a current control current source with the same ZF prime into YF as the current gain now, okay, instead of the voltage gain. So, one would say that it is enough if you have these two blocks realized, the other two blocks can be easily realized, okay. Whereas, if you have only the other two blocks, these two blocks cannot be realized. So, these two are more basic than the other two, even though other two seem to be more popular, right. These two, if you try to realize, it is possible to realize all the 4 types of amplifiers. So, it is necessary that these two must be studied and possibility of designing these two optimally should be investigated, so as to sort of unnecessarily not waste time on other two designs. Right. So, we have voltage control voltage source realized this way, current control current source realized this way, and therefore, we could say that these two amplifiers, ideal amplifiers, are more basic than the other two, which will be again discussed in terms of now what are the parameters. We have already taken I naught, Vi, V naught. On one side this will come, on one side this will come, interchange. Now, we will take I here and V naught here and vice versa, right. These are called hybrid mixed parameters. Now, will not have the same dimension, they will have mixed dimension, right. So, these are called hybrid parameters, H parameters or G parameters, okay. These two parameters we will discuss and see the various types of ideal sources which can be realized using this in the next class.